What's up, folks? Today we're going to be looking at 2.4, graphing a function rule. I'm also going to show you, so I'll show you how to do it by hand, how to graph things by hand, and then I'm going to show you how to use your calculators, your graphing calculators. So, AREI 10 is the Common Core State Standard. It says, understand that the graph of an equation in two variables is the set of all its solutions plotted on a coordinate plane. There's also discrete graphs and continuous graphs, which we will talk about as well. Okay, so it says the set of all solutions of an equation forms the equation's graph. So any thing that makes this equation true will fall on that graph of the equation. A graph may include solutions that do not appear in the table. A real-world graph should only show points that make sense in a given situation. So this one is just an equation. So first, we know this is in the form y equals mx plus b. So we know how to graph that pretty easily by hand. First going to make our graph here. Okay, we have y equals mx plus b, so we know that m is going to be -2, that's your slope, and b is going to be +1. So to graph a linear function in y equals mx plus b, we're going to start at b, which is our y-intercept at 1 here, and then we're going to rise -2. If I put that as a fraction, I just put it over 1. So I'm going to go down 2, so 1, 2, and I'm going to go right 1, and I'm going to put my point there. And then because I have 2 points, and I know this is a straight line, I can just connect them like so. Those were really close. It's kind of hard to graph on this. But I'm going to connect them like that, and then that's our graph. Okay. So if I test those points, if I plug in this point right here, that was 1, -1. If I plug those in, so -1 is my y, equals -2 times +1 was the x, plus 1. So I get -1 equals -2 plus 1. -1 equals, this comes out to be -1. So that is one of the solutions of that equation. So every point that falls on this line right here is going to be a solution to this equation. Okay, so that's how you can graph it by hand. Okay, you can also graph this on your graphing calculator by going like this. So if you have a TI 84 or 83, or basically any TI, this is how you want to do it. So, oops. So this is probably what your graph looks like, or your calculator looks like now. Okay, if you go to this y equals button right here, oh, you can't see my mouse. How sad. Okay, if you go to the y equals in the top left and click that, this one right here, takes you to this menu right here. So on that you can just type in what the equation is. So I can say -2x, not store, okay, x is going to be this button right here, the red one that's eliminated now. Why is it deleting it? -2x, okay, and then plus, was it -2 plus 1? Plus 1. So the x is the button next to the alpha. This is xt, there's a theta and an n there. So I hit that and then I go to graph. And this is error for some reason, but yours should be fine. Oh, because I put minus instead of negative. I have to use this negative sign next to the decimal on the bottom, next to the enter right there. Okay, then graph, and that's what our line should look like. Okay, and I don't remember what ours looked like. It did look like that, but that's how you graph it. You can also change your zoom by going here. You can zoom out, you can zoom in. Usually I like to go down to zoom fit. Usually zoom standard works just fine, which is what you're at right now. Okay, but if that doesn't work, sometimes we're going to use zoom stat. Other times you can just do zoom fit, which kind of changes your scale a little bit, but there's a bunch of different zooms you can mess with. Okay, so moving on. I'm going to have you try this one. So graph it by hand first, and then see if you can do it on the calculator. Okay, go ahead and pause this in 3, 2, 1, pause. Okay, so I graphed it on the calculator. We're starting at the y-intercept of -1 here, and then it's going up 1 and over 2. So rise 1, run 2, and then I'm right here. So it becomes this line right there. Okay, so that's what it should look like. Something like that. You can see the slope is positive. Okay, it starts at -1 there. And yeah. Okay, moving on. We have this real-world problem here. It says when you graph a real-world function, choose appropriate intervals for the units on the axes. Every interval on the axis should represent the same change of value. So you're going by the same amount in each time. If all the data are non-negative, only use the first quadrant. So if it doesn't make sense to have negative feet, we're not going to use all four quadrants, okay? So this one, it says the function rule W equals 146C plus 30,000 represents the total weight, W, in pounds of a concrete mixer truck that carries C cubic feet of concrete. If the capacity of the truck is about 200 cubic feet, what is a reasonable graph for the function rule? Okay, so again, this is linear. So we're going to start, it doesn't make sense to have negative weight or negative feet, so we're just going to look at this first quadrant here. This is the first quadrant, second, third, fourth. So we're really just focusing on the first quadrant. So I'm going to go up by, my x-axis can be 1. That's going to be our C, our cubic feet. Actually, I'm not going to go by 1 since it can go all the way up to 200. I know that's the max it can go to. So halfway is about 100. That's going to be 150, 50, so on. Okay, and I know that our y-intercept is 30,000, so I'm going to just skip up a little bit. So when you skip, you make this little indent thing right here. Say we're going to start at 30,000, 30K, and then just go up by, I don't know, 1,000 maybe. No, let's say like 35. Let's go up by 5,000, so 35. 40,000, 45, 50, and so on. Okay, so I would first start on my y-intercept, which is 30,000 right here, and then you're going to go up 146 and over 1. Okay, but because I'm going up by 50s, I'm just going to plug in some numbers. So 146 times 50, and I might need to change my graph after I figure this out, plus 30,000. Okay, if I do that, what do we get? Okay, so that should come out to be 37,300. Okay, so at 50, I'm up at 37,300, which is about right in between 35 and 40. Okay, and then I plug in 100, and if I plug in 100, I'm not going to write it out, I'm just going to do it on the calculator. I get 44,600, so that's going to be just below 45. So about right there. If I plug in 150, so 150 times 146 plus 30,000, it's just under 52, so 51,900, so just like up here, and then 200 is the max, so 200 times 146 plus 30,000 is almost 60, so it's like up here. Okay, I haven't gone that high on my graph, but so this is what our graph looks like, and you can tell that it is linear, which we know because there's no, it's in y equals mx plus b, or w equals mc plus b if you want to be exact in this one. But that is what the graph looks like. Notice I'm going to stop at 200, so I actually don't want this arrow because it's going to stop. You can't go above 200. So I'm just looking at that chunk right there. I'm not going to go back this way because that would represent negative weight or negative cubic feet. This is in weight here. Okay, so make sure that your graph makes sense when you do it. Okay, moving on. Okay, this one is talking about weight and gallons of water. So again, you can graph it. You only need the positive quadrant. And in this case, your weight would only, or your gallons would only go up to 250. So on the x-axis, your max would be 250. Okay, but again, it should look something similar. So I'm not going to do that one or make you do that one, just for the sake of time. Okay. All right. Moving on. Continuous and discrete graphs. In problem 2, the truck can contain any amount of concrete from 0 to 250 cubic feet, such as 27.3 or 105 2/3 cubic feet. You can connect the data points from the table because any point in between the data has meaning. Some graphs may be composed of isolated points. For example, in the Solve It, which I don't think we did, you graph only the points that are representing printing whole numbers of photos. So a discrete graph, that would be discrete. Discrete graph is when you can't really have any decimals and numbers in between, so you have to use like only whole numbers. For example, if I'm counting the number of children in a class, I'm not going to be able to have like 10.5 children. So only whole numbers make sense in that situation. So in that case, it would be a discrete graph, and we would just use the isolated points like this. Okay, but in a continuous graph where any number could make sense, like the concrete, you could have decimal amounts of concrete. you want to use a continuous as just a straight line like this. You are connecting all of the points. Okay, so let's look at a few examples, and then hopefully it will make more sense. Okay, so this says a local cheesemaker is making cheddar cheese to sell at a farmer's market. The amount of milk used to make the cheese and the price at which he sells the cheese are shown. Write a function for the situation, graph the function is continuous or discrete. So first, we know that 1 gallon of milk makes 16 ounces of cheese. Okay, so this wants two different things, right? It's asking for the amount of cheese he can make and the cost of the cheese. Okay, so first, this is going to be linear because each gallon makes 16 ounces of cheese. So it should be y equals mx plus b. If he makes if he uses 0 gallons of milk, it's going to be 0 cheese, so our b should be 0. So, and then it's going up 16 ounces each time, so it should be y equals 16x. Okay, in this case, can you use 1.5 gallons of milk? Well, in this case, yes, you can, because you can measure it out. You could use 1.25 gallons. So this one is continuous, because you can use any amount of milk, really. You could use 1 2/3, as long as you have that kind of measuring cup. So when you graph that, again, I'm only looking at the positive, but it should look something like this. So at 1, I'm at 16. At 2, I'm at 32, which we'll say is right there, and so on. But it is a straight line pattern. Okay, when you're doing cost, like this next one, it says each cheddar will cost $9. So, is this continuous or discrete? So, if you think about the equation here, it's going to be y equals, if you buy, it's going to be, goes up the same amount each time, so it's just going to be y equals 9x, because $9 per will is your slope. Your y-intercept is going to be 0. If you buy 0 wills of cheese, you're going to pay $0. So, y equals 9x. With this one, he could potentially sell half loaves of cheese. I don't think it says in the problem. Let's see. Okay, so if it did say that he only sells whole loaves of cheese, then it would be a discrete problem, because he could only do like 1, 2, 3. You could only do whole number amounts of cheese. But the cost, however, you really can only have a certain amount of dollars, because we're going to round to the nearest cent. So really, this is probably more of a discrete function. So you would, it's kind of hard to graph that though. So this is typically graphed as a continuous function, even though you can only have certain amounts of dollars. Your dollars are kind of limited. So it really kind of depends on this problem with what it gives us, and it doesn't really tell us anything. So assuming we can have half loaves of cheese or quarter loaves of cheese or just like an eighth loaf, maybe you can just sell like a slice of cheese like this. Then this really would be somewhat continuous, but if you think about the dollars, it's going to be discrete, but that's going to be a ton of points that you have to plot. So we'll just say this one is also continuous. And then we would graph that as well. Okay, looking at this, this is graph each function rule. We're going to skip that. So we're just going to say if it's discrete or continuous. The amount of water W in a wading pool in gallons represent, or depending on the amount of time T in minutes the wading pool has been filling. Okay, so how many gallons and time, how are those represented? So gallons, you could do a half gallon, you could do a quarter gallon. Oops, that's my alarm. I mean, school's almost over. You could do a half gallon or a quarter gallon, anything like that. Same with time. You could do seconds or milliseconds. You can keep going to like 3.5 seconds and so on. So this one's going to be continuous because we can use basically any amount of either of those. The next one here, B, says the cost C for baseball tickets in dollars depends on the number of N tickets bought, as related by the function C equals 16N. So in this case, you can't sell 1.5 baseball tickets. So in this case, this one is discrete. And when you graph it, you're just plotting the individual points. So let's just do like 1, 2, 3, 4. So one ticket's going to be $16. The next one's going to be $32, and then 48. So when you graph this, it would just be the points here. 1, 2, 32, 3, 48. and so on. And we're not going to connect these with a line because that would mean that we could have something in between 1 and 2, which doesn't work in this case. So this one we would just plot the points because it's discrete. You can't sell 1.5 tickets or 1 1/3 tickets or anything like that. Okay, and then the last thing, graphing nonlinear function rules. The best way to really graph these is just to plot a couple points, probably like 5 or so points. So the first one had the absolute value of x. So I'm going to plot maybe 5 points. I know this is kind of a longer video, but I'm going to plot some negatives and positives. So I'm going to start at -2, -1, 0, 1, 2. Okay, so if I plug in -2, absolute value of -2 is +2. 2 minus 4 is -2. So that gives us -2 there. Okay, next, if I plug in -1, absolute value of -1 is 1. 1 minus 4 is -3. If I plug in 0, that turns into a 0. 0 minus 4 is -4. If I plug in a 1, 1 minus 4 is -3. Then 2, absolute value of 2 is 2. 2 minus 4 is -2. Okay, and then we would just plot each of those points. So in this case, I'm going to use all 4 quadrants. And just plot each of those points individually. So -2, -2 starts right here. -1, -3 is right here. 0, -4 down here. 1, -3. 2, -4, or 2, -2. So it's this V shape. And that's actually how all absolute values are graphed. They're all with V shapes like that. Okay, so you could always graph that, or you can graph it on your calculator. I'm not going to show you how to find the absolute value on your calculator right now, though, because we're below 110. Okay, the next one, y equals x squared plus 2. So again, if you don't have your calculator handy, you can just plug them in. So I'm going to use the same 5 points. If I plug in -2, -2 squared is 4. 4 plus 1 is 5. If I plug in -1, -1 squared is 1. 1 plus 1 is 2. 0 squared is 0 plus 1 is 1. 1 squared is 1 plus 1 is 2. 2 squared is 2. 2 squared is 4. 4 plus 1 is 5. Okay, so then we plot those points. 1, 2, 3, 4, 5. And it looks like this. So -2, 5 is up here. -1, 2 is right here. 0, 1 right there. 1, 2. 2, 5. So this is more of a U shape, not really a V shape. So whenever it's x squared, it's always going to be that U shape. Call that a parabola. Okay. And that is probably the best way to graph these unfamiliar functions. If it's not linear, just plug in probably 5 or so points. Same with this one. I'll quickly do it on here, so you can pause this, and then you can check yours. So pause this in 3, 2, 1, pause. Alright, so I use those same 5 points again, the x's, and plotted my points, and I got this. This is a cubic function, looks like this. So, yeah, that's what that should look like. Sorry this video is longer than it usually is. But that's how you graph things. You can also plug it in your calculator to check that. But yeah, make sure you do the Canvas quiz, and I will catch you on the next one.